Okay, integration by substitution. These kind of problems take a lot of practice. Once it clicks, though, it will click forever, but you're going to have to do several before it completely clicks. And some of these, there are two different ways to approach integration by substitution. The way I like is forcing du. The other way I will call solving for dx. And I'll do some of these problems both ways. Pick the way you like and then always do it that way. What is integration by substitution? It's chain rule backwards. That's literally all this is. Instead of taking a derivative and using chain rule, we're forcing something to look like somebody already used chain rule and then doing an antiderivative. So integration by substitution works when you have a function inside a function, you already have a composition, and you magically already have that inside guy's derivative sitting inside your integrand. So this, look at that. That looks like somebody's already done chain rule on something. Then we'll call this guy, usually we call this u substitution. We'll call g of x u. Then this here will be du. And then we just need to know the antiderivative of f of u du. So whenever here's kind of a guide for integration by substitution, we're going to notice that we've got a function inside a function. We're going to figure out who our inside guy is and make sure that his derivative is sitting inside the integral. And then we're going to do a substitution. Let u be the inside guy. Replace everything with u's and du's, and then integrate. And hopefully we know the antiderivative of whatever we write. If we don't know the antiderivative of what we write, we just wasted our time. Okay, this will make more sense when we do a few examples. Okay, so I want the antiderivative of cosine of 3x. So I've got a function inside a function. Okay, so I said I was going to do this two different ways. This is my way, the du method. So I'm going to call the inside u. U equals 3x. Then du, the derivative of that, I'm taking the derivative with respect to x here, will be 3 dx. So what I've done here was I took the derivative with respect to x of both sides here. Another way of saying this is du dx, the derivative of u with respect to x is 3, and think of it like I multiplied this dx over. Okay, now I'm going to, this is called integration by substitution for a reason. I'm going to substitute these things in. So instead of writing cosine of 3x, I'm going to write cosine of u. Now, I have to have in front of me du. So I would like to see written in front of here exactly this. I want to be able to write a du here. You can never, ever, ever in your life have an integral symbol without having the appropriate differential here. I cannot do this integral if I don't have a du sitting here. Do I have du in front of me? Du is 3 times dx. I really wish I had a 3 sitting here. I'm going to put 1 in. Oh, now I've just made stuff up, though. I just made up that 3. In order to counteract that, I'm going to put a 1/3 in also. Now, notice I put that 1/3 outside. That's a constant. So really, all I did was multiply by 1. You could think of it like I did this. I'm going to put a 3 over 3 here. Why did I put a 3 in? Because that right there is du. And then I take this 3, this one on the bottom that I don't want, and I put it outside instead. So this is u right there. And 3dx is du. And where did that 1/3 come from? I needed a 3 inside here so that du was sitting in front of me. In order to get that, I had to put in a 1/3 also to cancel out that 3. Now this I know the antiderivative of cosine of u, that 1/3 comes along for the ride. Antiderivative of cosine of u is sine of u plus c. But I know what u is. U is 3x. So there's my antiderivative. How could I check that? By taking the derivative. What's the derivative of sine of 3x? That's chain rule. I've got a function and a function. Derivative of sine of anything is cosine of the same thing times the derivative of the inside. Derivative of 3x is 3 times 1/3. That'll cancel out that 1/3, leaving just cosine of 3x. Okay, every one of these I'm going to do both ways. This is the way I prefer. Force the du to be sitting in front of you by putting in and taking out whatever you have to. Here's an alternate approach. It's the same math, but sometimes people understand this approach a little better. So call u 3x. Then du, take the derivative of this, that'd be the derivative of u with respect to x times dx. What's the derivative of 3x? 3 dx. And then this approach is solve that for dx. Get that dx by itself. So du over 3 would be dx. And now we make 2 substitutions. Plug in this for u, that's going to go right there. Plug in this for dx, that's going to go right there. So I'll get the antiderivative of cosine of u, that's u. Dx is du over 3. That 3 I can pull out front. And now we're in exactly the same place we were right there. Antiderivative of cosine of u is sine of u plus c. And then our answer is never going to have u in it. What was u? That was just a dummy variable I made up to help me do the integral. I always have to go back and substitute back in at the end. U was 3x. Okay. Let's do another one. We're going to do a whole, I got like 10 of these prepped for today. Okay, this guy here. I've got e raised to some power. If I just knew the antiderivative of this, I would just write it. If I knew the answer, I would just do it. But I don't know the antiderivative of e to the 9x. That's not in my integral table formulas or table of formulas. So this is e raised to some junk. I'm going to call that junk u. Again, just like before, I'm going to do this both ways. Then du, the derivative of this would be 9 times dx. I'm going to make 2 substitutions. It's always 2 substitutions. This is u right there. I need this to look like du. I need this. I have to have this sitting in front of me. I don't have a 9 sitting there. Well, I'm just going to put one in. I'm going to put in a 9 there. I'm allowed to do that as long as I also put in a 1/9 out front. See, now I haven't changed anything. Then this is u, and that right there is du. Then this integral, that 1/9 comes along for the ride. This will be e to the u, 9x was u, and that 9 dx becomes du. I know the antiderivative of e to the u. That's e to the u plus c. But what was u? U was 9x. And if you want to check that, take this guy's derivative, see if you get back the original. Do you get e to the 9x? Yes, you do. Okay, same exact problem, only now this time I'm going to do it by the solve for dx method. Personally, I don't like this method, but some students prefer to do these this way. So we start the same. U is 9x. Du will be 9 dx. So du is always this. Remember, we covered differentials 6 weeks ago. Du is the derivative of this thing with respect to x times dx. Don't forget the dx. Let's solve that for dx. To get that dx by itself, that would be du over 9 equals dx. Now I make this substitution, plug that in right there. And this substitution, plug that in right there. I'll get the antiderivative of e to the u, because that's u. And dx was du over 9. Now I got to pull that 9 out front because it's a constant. I'm allowed to do that. And it's in the bottom. Now I can do this antiderivative. I know the antiderivative of e to the junk, d junk, is e to the junk. Plus c, don't forget your plus c. And then your final step is always substituting back in whatever u was. So the two approaches are find du and make sure you're only allowed to do this by multiplying and dividing. You can't do it by adding and subtracting. By multiplying and dividing or dividing, force your du to be sitting in front of you. The other approach is solve for dx and substitute that in, but then you're probably going to have to pull something out of the integral, some constant, and you got to be really careful that you put it either on the top or the bottom, wherever it goes. Okay, we'll do one more in this video, and then I'll do a new recording. Okay, let's look at this guy. Think about this for a minute. You're allowed to split up numerators. If I had something like this, I'm allowed to split that up like that. You're allowed to split up numerators, right? Each one over the denominator. You cannot ever, no matter what, you can never split up a denominator over addition or subtraction. You cannot write this over that, or this over that, plus this over that. You can't split up a denominator. That's not how fractions work. So I have to look at this and think, okay, what could I possibly call u? And if I call something u, will I have du sitting in front of me? So you might try maybe u equals t to the 5th plus 9. The denominator there. I'm calling that u. Why did I do that? Because du then will be 5 t to the 4th dt. Do I have that sitting in front of me? your entire du better be sitting in that integral somewhere. It almost is. I've got the t to the fourth up on top, but I don't have a 5. I've got a 3 instead. How could I change this into a 5? Well, first I could pull that 3 out. It's a constant. I'm allowed to just pull it out front. And now if I wanted to, I'm allowed to just put a 5 in here, as long as I also put a 5 out here. Say, look, I haven't changed anything. This, what I've written, is exactly the same thing I started with. But now look what I have. Up on top, right there, that is exactly, right there, is exactly du. And the bottom is exactly u. So I could rewrite this, if I wanted to, as 3/5 the antiderivative of du over u. Do I know the, see, if I get here and I don't know the antiderivative, then that didn't help me. But I do. I know the antiderivative of 1 over u du. That's what this is. That's 1 over u du. Like we just talked about that in the last video. That's the natural log of the absolute value of u. The antiderivative of 1 over u du is ln of absolute value of u. But what was u? U was this. And then don't forget the plus c. How could I check this? Take the derivative of this. Like, try this on your own. Really, right now, pause. Take this guy's derivative. See if you get this. You will. How did I know to use the entire denominator for u? How did I know I didn't just want this? Then du is still 5t to the fourth. If I tried that, then I would have something like this. I don't know the antiderivative of 1 over u plus 9 du. I don't know that guy's antiderivative. That's why I chose to do the entire bottom as u. So you look at this and think, do I look in your integral formula or table of formulas? You don't have anything that looks like this. Now this one, we could actually do another substitution on this. Like, there are ways to do this using substitution, and you'll still get the same answer. But the key to doing integration by substitution is to pick for your u something whose derivative is already sitting there, and if you fudge the numbers a little bit, and something that takes up some space, something that is an entire denominator, maybe something that's already sitting in an exponent, something that's in parentheses. There's no rule when it comes to integration by substitution for what you have to use as u. A lot of these take some trial and error. And a lot of times you'll try one and go, oh, well, that didn't work. And so you try something else for u. All right, let me get rid of all the stuff that didn't work. And for fun, let's do this same one using the other method. So same problem. I'm going to let u be t to the fifth plus 9. du is 5t to the fourth dt. And I'm going to solve this for dt. Again, I don't like this method, but some students like it. dt will be du over 5t to the fourth. So I'm still going to substitute in this, plug that in right there, and I'm going to substitute in this. So I'll have the antiderivative. I'm rewriting everything else. This is u. And then dt, I'm going to write all this stuff. And notice the t to the fourths cancel out. I get a 3/5 there that I could pull out. And I'm left with a 1 over u du. I get exactly the same antiderivative I got before. So this method is solving for dt or solving for dx. It'll work, but it tends to lead to more confusion, I think. Remember, when you finally get to an integral, when you're ready to do an antiderivative, you cannot have two different variables floating around. Everybody's got to be u's. You can't have t's and u's and then do an integral. Somehow you have to have converted over to just one. So if these t's hadn't canceled out completely there, I was in trouble. But luckily they did. Okay, let's stop this one. I'll start a new video.